Just a few more things to wrap up about the idea of interfaces and programming to an interface, and then we'll start with our first actual official data structure. So, right. So one thing that I said earlier was that interfaces didn't contain any code, right? So that interfaces just defined a contract of public methods, and that classes implemented one or more interfaces. And this was part of the principle of encapsulation, right? Separating your external behavior, your interface, from your implementation. And the idea was that by doing so, by defining an abstraction as an interface, right, as our abstract data type, that's what embodies our abstract data type is the interface definition, then we could have more than one implementation of that interface. And we could, and anybody or any code that needed to work with an object that implemented a particular interface could program to the interface and not have to worry about the implementation. And the implementation could get swapped out underneath it without anything having to change because I'm programming to the contract that the interface specifies, and the class satisfies that contract. And so an object of a particular class that is being used for a particular interface works just fine. So, what I initially said that the interface only had a listing of public methods available and did not actually have any code. Well, that actually is not technically true. It turns out that you can, in an interface, define static methods and fields. And that kind of makes sense, because remember, static means it belongs to the class as a whole. So same thing. You don't need an instance. And therefore, if you have helper functions or other fields or values that are associated with the abstraction as a whole, then without necessarily needing an instance, then that's OK to define in the interface so that you can, like you can with class static methods and fields defined in classes, just go through the interface name to get to those methods and fields, right? And so, right. But the other thing you can do, which is kind of cool, is you can, in an interface, and this is it breaks the prior statement that there's no code in an interface, you can define instance methods in an interface as long as they only use other instance methods in the interface. In other words, if you have a method in an interface that can be completely specified and implemented with respect to the other methods in the interface without needing to get to instance fields or implementation-specific stuff, then you can do that, right? The syntax of it is by specifying the method in the interface with the keyword default as a default method. And we can see an example of that in our last lecture examples. If we look at point, right, which is, right, so if we look at point in our last example, a point is something that could get an x, get a y, calculate its distance to some other point, and calculate whether or not it was equal to some other point. Well, if we look at our two implementations, remember the last time we left this example, we had two implementations of this interface. We had Cartesian point, and we had polar point. And the idea here was that we could use either Cartesian points or polar points when creating our triangles because it didn't matter as long as they were points. So we had P1 and P2 as Cartesian points, P3 as a polar point, and that's fine. We could give all three of those points to our point triangle in order to get a triangle. And our triangle was also an interface, right? But if we look at Cartesian point and we look at distance 2, we can see that the only thing that distance 2 requires is to be able to use getX in order to retrieve the x value of my own point, and to use getX as a method to retrieve the x value of the other point. So in this expression here, which is the calculation of the distance between one point and another point, we don't actually refer to x or y directly because we're just going through getX, which is a public method of points for both ourselves and the other point. Similarly, for equals, same thing. We're just using our own getX to retrieve our x value. and the other points getX to retrieve the other value, and we compare it against this static field point epsilon, which is a named constant, in order to then decide whether or not we're equal. If we look at the same definitions inside polar point, they are exactly the same. And the reason why they're exactly the same is because they don't do anything implementation specific. There's nothing specific to whether it's a Cartesian point or a polar point that affects how we're implementing distance to and equals. This is a perfect opportunity to rewrite this example as a default method, right? So, for example, we could, and now I'm moving to the lecture 8 examples, we could rewrite this so that point as an interface defines our named constant point epsilon for how close things have to go, because we can put static fields in an interface. And we could define distance to and equals as default methods. So here we have an interface definition, which means it has no fields, it has no constructor. I can't say new point. I have to say new some kind of point. But there are parts of this interface that can be written in terms of the other parts of the interface. And anytime you can do that, you can implement that as a default method. So here's our distance to, and instead of it just being a declaration of an interface method, it actually includes code for calculating the right value. And it can do so because it's only using the other parts of the interface. And so the syntax here is, it looks like a method definition, but it has to have this default keyword. And the nice thing is that once I have a default implementation of distance to and equals in my interface, then any implementation of that interface does not have to provide their own version. They get the default version. They can provide their own version, in which case they'll use their own version rather than the default one of the interface. But if the default one from the interface is good enough, then the implementation specific, the implementing class does not actually have to provide these definitions, because a default definition for these methods is available. So Cartesian point now just becomes the stuff that isn't available, right? So in a point, we need something to tell us what our x-coordinate is. We need something to be able to get our y-coordinate. So those things are not specified as defaults, right? That's an implementing class has to provide that. But distance to and equals have default implementations. And so Cartesian point can just fill in what's missing, the getX and getY, in order to implement point, and does not have to provide distance to and equals, because it will get those from the interface as default implementations. Same thing with polar point, right? Now polar point just has to do its implementation-specific getX and getY. It doesn't have to do the equals and distance to part, because that's part of a default implementation in the interface. Okay, so a quick recap of what interfaces are and why we want to use them. They are a contract for behavior. It specifies a set of method signatures that an implementing class has to provide. It defines the data type, right? Relative to data structures, an interface is essentially the definition of an abstract data type. It's abstract because it does not specify how it's going to actually implement any of this. It just says, this data type has these methods, and you can work with a instance of this data type using these methods, right? You still need to have a specific class that provides the actual internals, right? All of the methods that don't have default implementations, and any fields, that instance fields that require that that is the data that is required for that implementation, as well as constructors, so we can create new versions of it, right? Okay, so when we have an interface, right, we can create an object that can be treated as an object that implements that interface, right? So here, for example, is a little example where we've defined some interface called media, and media says, okay, a media object can get its length in seconds or get its length in minutes, or let's say it has a rating that you can either get or set, and it can retrieve its name, right? That is what a media object needs to be able to provide. And now we might have two specific implementations of this media interface. We might have song objects which implement media, and we might have video objects that implement media. And so those classes, by declaring that they implement media, are basically promising that they will provide the appropriate implementations for all of those methods in that media interface. So this relationship between a class and the interfaces it implements, right, has is referred to as an is-a relationship, right? And that's actually how people talk about it, right? It's a little not technical, but it's that's a is-a relationship between two types, between a class and an interface, for example, is basically declaring or kind of indicating that the first thing, right, can be treated like the second thing. So when a class implements a interface, we have an is-a relationship between that class and that interface. So that an object, an instance of that class, is a instance of the interfaces that class implements. Right? And so this is a form of what's known as polymorphism, where an object can be used as an instance of some other type that it has an is-a relationship with. So I need an object that is a media type, or I'm working with an object because it's a media type, because it implements an interface, and the actual object has a specific class that I use to create it, and so that object has, obviously has an is-a relationship with its own class, right? I mean, if I create a song, then that song object is a song. That's just by identity, but it also has an is-a relationship with media and can be used anywhere where media is expected. So, this assignment is allowed across an is-a relationship, and this is part of programming to an interface. You want to program to the interface that you're using that object for, right? So if I create a song s equals new song, and I have some media reference m, then it is okay for me to say m equals s, because now m refers to the same object that s refers to, and that object, because it's a song, has an is-a relationship with media, and so that's fine, right? Same thing, I can create a new video object, and I can assign that video, I can assign a media reference to that video object, or pass that video object to a method that is expecting a media object as a parameter, or otherwise use that video object wherever a media object is expected, because video has an is-a relationship with media. What I can't do, obviously, is if I have a video object, right, and then I have, let's say I create a video object and have a reference to it through the name v, which is type video, and I have now a name song, s, which is of type song, I cannot assign s to v, because while the two classes, song and video, both happen to have is-a relationships with media, they do not have is-a relationships with each other. Okay? So yes, a video object is a media object, and yes, a song object is a media object, but that does not mean a song object is a video object or vice versa. Right? And that kind of makes sense, right? So just because two things have a relationship with a third thing does not mean they necessarily have a relationship with each other, right? So a lion is a mammal, and a tiger is a mammal, but a lion and a tiger are not necessarily a lion isn't a tiger and a tiger isn't a lion, right? So that is a relationship determines when I can use a reference to an object in a particular context. Is there an is-a relationship with that type, with that interface? Then I can use that object. Right, and so we want to program to interfaces because we want to refer to objects through the interface that we're using them for, and that is most appropriate for the purpose for how we are using that object, right? When we do so, it limits our view of the object to just what that particular interface provides. So if we have a song which is a media, it might also have, in addition to the methods it needs to have in order to be a media object, it might have other methods that are part of being a song object. But when I have a reference to that object through the type media, my view of that object is constrained to just what the interface says it has, right? So the actual object that I'm referring to might implement more than the interface that I am using it for, right? It could also implement some other interface or have other public methods that are available through its class type. But because my reference to it has a particular type as a media object, I am limited in my view of that object to just what that interface declares. And that's a good thing, right? Because it prevents you from accidentally using parts of that object that aren't media part of being a media object, right? And limits bugs when you really are trying to deal with an object just because it's a media object or through things that should be part of its implementation of the media interface. You want to reduce your view of that object to just the interface you want or need so that, one, you can use other kinds of objects that also implement that media in that same context without worrying, because you don't care what it really is, you just care that it's a media object. But two, it prevents you from making an assumption or accidentally starting to use parts of that object that are not part of its implementation of the interface that you wanted it for. Right, so we can actually define interfaces relative to each other. So we can take an existing interface and define a new interface which extends the existing interface. In other words, we can define an interface that says, okay, look, I'm exactly like some existing interface, but I want to add additional behavior to the contract. So I am a media object, but I'm also want to add some additional public methods, and I want to call this new interface something different, which basically assumes all the stuff of the prior interface, of the existing interface, but then adds new stuff. This is actually a form of an inheritance which we're not going to get into in detail, but other than to understand this relationship between an interface and an extended interface. And so the original interface is sometimes known as the parent interface or a super interface, and the new interface that extends the original interface is sometimes known as a sub interface or a child interface or an extended interface, right? Those are all just kind of nomenclature. And the way we create these new interfaces based on existing interfaces is with the extends keyword. So for example, I can create a new interface called compressed media, which extends media and adds the following three methods to the contract, right? It says, oh, get compressed size, get uncompressed size, and maybe if I can uncompress I need to be able to uncompress the media object and turn it into a new uncompressed media object, return a media object which is the uncompressed version. Right? Maybe those are the three things that a compressed media object can do. Now, a compressed media object also can do everything a media object does, and and anything that claims to be a compressed media object has to provide both. And the reason why is because we've declared compressed media as an extension of media. So we're basically, it's almost like we've copied and pasted everything in media into this new interface and then added some new stuff. And because in order to just prevent ourselves from having to type, we can just say, oh, we extend this existing interface. Everything that's in that existing interface, yes, we're going to do all of that, and we're going to do this other stuff as well. All right? So that kind of extension starts to create a hierarchy, right? If compressed media extends media, then everything that is a compressed media also is a media, right? And we can think about is-our relationships up that hierarchy. right? So if I have now a song that implements compressed media, that song object also needs to implement all of the media stuff, because compressed media is an extension of media. And so a song object now has an is-a relationship both with compressed media, because it's declared as implementing compressed media, but it also has an is-a relationship with media, because compressed media extends media, and because the virtue of that extension, anything that implements compressed media has to have everything that media has, and we can use a song object anywhere that is-a relationship is valid. And I know it's valid for compressed media because it's in the declaration, but I also know it is valid for media because when I declared compressed media, I declared it as an extension of media. And by that transition through the hierarchy, right, a song object also has an is-a relationship with media. So if I have a song object and I use it in the second line where I say compressed media CM equals S, that's okay, because that object S has an is-a relationship with compressed media, and so I can use it as the target of my assignments of CM, because I need, on the right-hand side, something that is a compressed media, and song has an is-a relationship with compressed media. But it's also okay to use song anywhere I need a media object, because compressed media extends media, right? Now, if I happen to have if you need to go backwards across the is-a relationship the opposite way, right? In other words, I have something which is a media object, and I just happen to know, just because of the way the program works and the logic of it, as the programmer, I just know that this media reference is in fact a song, and I really need to get to some of its song-specific stuff that is not part of the declaration of a media interface, and I really want to turn that reference back into a song reference instead. I can do that, right? I can try to do that by what's known as casting. And casting is essentially where I take a type and put it in parentheses in front of a reference, and essentially I'm asking the compiler, please take a reference to some object that, and turn it into, or treat it as if it were this other type instead. And so if M really is a song, then it's okay to turn M back into a song by casting it into a song. Now, the compiler can check is our relationships going the correct way. So those first few lines, right, where we say compressed media CM equals S, I didn't have to specifically turn my song into a compressed media because that was the natural way of doing things. In other words, the compiler, because of the way things are declared, already knows that a song is a compressed media, and so can check to make sure that the thing on the right-hand side really is the right type of thing for what you're assigning it to, and and everything's fine, right? But if I do want to go from something back to a more specific type, in other words, I have something that is a media, I know it, but I also happen to know that it really is a song, and I'm going to force it. I'm going to ask the compiler, please treat this object as if it were a song, right? I can try to do that. I can write that code on this last line in order to take that media reference and turn it back into a song reference. And it will be fine as long as it's actually true when I run my program. So the compiler can't complain about it in advance because I put the cast in front of it, and so I'm saying I know what I'm doing, right? I know that whatever M points to is not just a media object, but really is a song, and I want to force it to become back into being a song, right? And the compiler will trust me. It will take a look at this code and allow me to write that code, and it will try to do this because I have expressed that is okay. But then when you actually run the program, and you get to that line of code, if whatever object M is pointing to really isn't a song, that's when your program will fail. So you can cast a reference backwards across an is a relationship the other way, but there's no way to check it at compile time that it's true, and at runtime, if it's not true, it'll cause a problem. Okay. So when do you extend interfaces, and when do you just because remember, a class can implement as many interfaces at once. So I can have a song be a media, and I can have a song be some other kind of interface. Maybe a song has an x coordinate and a y coordinate. You can calculate its distance to another point. Hey, then a song is a point, right? I mean, so I can declare however many and whatever the appropriate interfaces are implemented by a particular class, right? And I can treat that new object or that object as any one of its interfaces because it has an is-a relationship with all of its interfaces. So when do I choose to extend an existing interface versus create a whole new interface with the additional stuff and just add it to the list of interfaces that class implements? Well, that's a matter of design, right? In general, you should extend interfaces to create a new interface only if the new stuff doesn't make any sense unless it also has the old stuff, right? So it doesn't make sense for a object to have all the methods of compressed media unless it also has all the methods of media, because maybe it just doesn't make sense for something to be a compressed media without being a media. In that case, it makes sense to define compressed media as an extension. But if these things are largely independent of each other and there are just different facets of behavior, and an object can have some subset of different facets of behavior, then it makes sense to define these things as separate interfaces, and then for any particular class to simply list which ones it's going to be able to abide by. So an alternate view, for example, might be something like this, where I have a media interface for things that can be media, and I also have a compressed interface for things that are compressed. And maybe some things are compressed but not media, and maybe some things are media and not compressed, and maybe some things are both. They're both compressed and media, right? If that's the case, if that's the situation, then it's better just to define these things as separate interfaces. Neither is an extension of the other, and then when I have an object type, when I have a class that properly implements both interfaces, simply list both interfaces in the list of interfaces that class implements. And then I can use it again, so now my song object has is-a relationships with compress, and my song object has an is-a relationship with media, and I can use that song object wherever I need a compressed object or wherever I need a media object because those is-a relationships exist. Okay. So let's do a little call and response here, right? Let's say our situation is like this, where we have our interface media with all these things, and we have our interface compressed, and we have a song class that implements both compressed and media, right? So now we start at the top of our little example code. We've created a new song object that we have a reference to in S. And now I'm asking, can I call getCompressedSize on using my reference to a song, right? So for this for this first one, if we think that's okay, that's going to be go, and if we don't think that's okay, it's going to be heels, right? So on 3, we'll do all our goes, and then after a beat pause, anybody who thinks it's heels. So if it's okay, go. If it's not okay, heels. 1, 2, 3. Yeah, that's right, because song is, right, song is the class, and it has both compressed and media, right? So if I have my reference through song, then yeah, sure, I can get to get compressed size because song implements compressed, and get compressed size is one of the methods that song must implement in order to make that that statement true, and things are good. Similarly, get name, no problem, right? But now let's say we take our song object S, and now we put it into a context where we've limited its view to just media. So I say media M, so M can only point to media things, equals S. S happens to be a song object, and that song implements media, so that's okay. I know that'll work. But now I'm going to have m.get compressed size, right? Is that okay? So so again, go is okay, and heels is not okay. On 3, 1, 2, 3. Yeah, that's right? Because now my view of that song object, even though it's the same object, and we just said before that that object has get compressed size, it has that method, right? But even though it's the same object, my view of it now has now been narrowed to just the media stuff, and the media stuff does not have get compressed size. Only the compressed interface has get compressed size, which is why the second thing, get length in seconds, will work, because that's part of media. Right, so I can take that exact same song object and now refer to it through a compressed reference C, right? And I think you guys get it. If I say ask for get compressed size, yes, that's going to be okay, because get compressed size is part of the compressed interface. But now get rating won't work, because that is part of the media part, and my reference to it is through C, which is just the compressed part, right? And so then if I take C, which was set to that song S, and try to turn it into a media, right? I say, if I say media M2 equals C, that actually won't work, right? And the reason why that first line doesn't work is because, yes, that song object does happen to implement media, but that line can't be checked by the compiler. Just because something is compressed doesn't mean it's a media object, and therefore, that line, the compiler is going to complain, because it's going to say, yeah, maybe that object is also a media object, but I don't know that it is. I can't reason about that relationship, and therefore I can't allow that line of code to be there. But that last line of code, where we take that compressed that reference to our song object through the type compressed C, right? I'm casting it to be a media. I'm basically saying, look, I know that it's a media object, that it's really a song object, which also is a media object, and that's going to be okay, right? So that last line, the compiler can't tell me that it's okay, but it won't also tell me it's not okay, because it's basically trusting the programmer. So the first version is asking the compiler to check, right? Without the explicit cast, it's basically saying, well, the compiler, you should be able to figure out whether that's okay. And if it's not okay, if it's not guaranteed to be okay, the compiler will complain. The second line, the last line, it's basically saying, look, I'm in control. I know that this, whatever C is pointing to, also happens to have an ISA relationship with media, and I am telling you it's going to be okay. Just trust me. So the compiler will let it happen, but then when it actually runs, that's when, if it turns out not to be the case, that's when you'll get in trouble. That's when your program will die, in a big exception, because you've taken something and forced it to be something that it can't possibly be. But if it is okay, like in this case here, because we know that the object being referred to happens to be a song object, and song has and is a relationship with media, then when it gets to that line, it will work and things will be fine. Okay. Now, contrast that to this situation where I've defined media as an interface, and now I've defined compressed as an extension of media, right? Now, the first two lines are obviously okay because song has everything, and I'm using the, S as a reference to song, and so, it has everything song provides, so great, right? And I know that since song implements compressed, and compressed extends media, I know that song must also implement everything in media, so those first two lines are fine, right? And now when I have a reference to S via the media type M, right, then I can't, right, and then my view is narrowed. So again, this won't work, right, because just because I have a reference to an object that is media doesn't necessarily mean it's compressed, and therefore I can't get to M that get compressed size may not work, right, or doesn't work, right, because my view of that object is now limited to just media, right, but M get length in seconds, that works because that's part of the media interface. Now if I take that same song object and I refer to it through the compressed interface, then yes, I can get its get compressed size because that's part of the compressed interface, but I can also get to its rating. And the reason why is because compressed is an extension of media. So everything that was in media is also, you have to think of it as also being part of being compressed. And so get rating, even though there isn't declared in the compressed interface, right? That's okay because compress is defined as an extension of media. Anything that is in media is also available through the compressed interface. So even though my view of the song has been narrowed to just the compressed interface, that doesn't mean it's just the things that are declared here in compressed. Because if it's an extension, it also includes everything that was declared in media. So my narrowing of my view of the object to compressed, because compressed is an extension of media, includes both the things that are declared in compressed as well as the things that were declared in whatever it's extending. And I can have extensions on extensions on extensions on extensions, and those is-a relationships, and whether or not something is available travels up that hierarchy. Now this last, let's go ahead and do the call and response for the last one. So in the last one, I have my reference to my song object via that compressed interface, C, right? And now I am asking, I'm basically assigning this other variable that has type media to something that to my reference to that song object via the type compressed, right? So if it's okay, we'll say go. If it's not okay, we did it the other way around, right? If it's not okay, we'll say go. If it's okay, we'll say heels on 3. 1, 2, 3. Oh, people are a little less sure, right? So what's going on here, right? Well, my C, right, is a reference to a song object and is of type compressed. Okay, that's fine. But remember, compressed is, in this example here, an extension of media. So there's an is-a relationship between compressed and media. Anything that's compressed also has to be a media. So that will work just fine, because the compiler knows that compressed extends media because it's in the declaration of compressed, and therefore it can check and it can verify that relationship, that is a relationship, and it will be just fine. So yeah, no problem. I can take anything that's compressed and use it anywhere I expect a media object because compressed is an extension of media. It turns out you can even define interfaces that are extensions of multiple interfaces. All it means is that you're taking all of those parent interfaces and you're unioning them together. You're basically munging them all together as part of what this extended interface provides, right? And of course, that extension can also add its own methods that are not part of any of those existing interfaces on top of that, right? So interfaces can extend more than one other interface. So we can have, this is what's known as multiple inheritance. And in Java, it only works for interfaces. You can't have multiple inheritances for class. We haven't talked about classes extending other classes, and we're not going to, because that's kind of an object-oriented 401 kind of thing, which you'll learn in 301. We just need this notion of interfaces, and so that's why I'm kind of going through interfaces and how they work in Java. So extending multiple interfaces in Java is allowed, and it just means that I'm going to union together all of the methods from all of the things that I've put together. This is very useful if you have a whole bunch of interfaces that define little aspects of behavior, like, oh, here's an interface for being compressed. There's an interface for being audio, or a media object. There's an interface for being something else. I don't know, rateable or comparable or whatever. And so you have a whole bunch of interfaces that define different sets of behavior. And now you need a new type, which basically says, look, I need a new type name for objects that specifically implement, interface A, interface B, and interface C. And it might be that I want that type name because I want to develop a method where I'm going to accept a parameter, and that the thing that is being given to me, I'm going to rely on that object having all three of those interfaces implemented. Well, if those are three separate interfaces without an ISO relationship to each other, I have a problem if I can't create a new interface, which is the combination. Because what do I choose? How do I type my parameter, right? If I need something that is an A and a B and a C as my parameter to the method, then if I type it as A, then someone might give me an A that isn't a B or a C. If I type it as B, then I might get something that is a B, but it's not an A or a C, right? And if I type it as a C, then again, I might be able to be given something that's a C, but not an A or a B. And I want to force the issue. I want to say, hey, look, I need something that is an A, a B, and a C, but these are three independent interfaces. The solution is to define a new interface. Let's call it ABC, right? Which extends A and B and C. And now I have a new type name that I can say, aha, my parameter is an ABC, and it's, and whatever you give me has to implement A and B and C because, it's ABC is an extension of A, B, and C. And because I have this new interface name that is an extension of all three interfaces, then I can use that type name in order to demand an object that implements all three interfaces. All right. One last thing before we get on to list, and that is the type object, right? So there is a special class called object with a big O that is the universal reference type. An object, right, has an object with a small o, like any given object, has a is-a relationship with, one, its own class. That's obvious, right? Two, any interfaces that the class implements, and of course, any of their parent interfaces and so on and so forth. That's what we just talked about. But it also has an is-a relationship with object with a big O. So object with a big O is a special class that is, that every object has an is-a relationship with. Because every object has an is-a relationship with object with a big O, when you need a reference that is going to point to an object, but you have no idea what kind of object it's going to point to, but you want to be able to point to any kind of object, that's the type you can use. If you use object with a big O for that reference, then you can assign it to any object of any class, because every class has an is-a relationship to the type object with a big O. Right? So it's kind of the type version of null, which is a value, right? If I can assign the value null to any reference, because null is the universal reference value for not having a value, right? Object with a big O is the universal reference type, where any object can be assigned to something that has been typed as object with a big O, because every class has an is-a relationship with object with a big O. Okay. Okay, so that's so that basically is our the last I'm going to say about interfaces, and and now what we're going to do is go to our very first actual data structure, right? So we had a reading. You should have read the chapters 1 and 2 of Think Data Structures, where they kind of talk about lists and the difference between array lists and linked lists, and why, and this whole idea of programming to an interface came up in that, right? And so, what is a list, right? We know what an array is. Array is an actual structure in memory, right? That's a specific structure in memory. It's contiguous, and it's fixed in size, right? But a list is an idea, right? It's an abstract idea. It's an abstract data type. An array is an actual specific kind of class of things, right? It's basically continuous memory that holds some number of a particular kind of object, right? Whereas a list is a structure that can be defined by its behavior, and we can implement a list in more than one way. This is why we're going to talk about list as an abstract data type, as an interface, and then talk about its implementation and see that our implementation choice has implications for how much memory gets used, what its performance is like, which operations, like how fast different operations take, right? Those are all implementation-specific details of an implementation of a list as a data type, as an abstract data type, right? So list is probably the very first and oldest data structure that's in computer science, right? And basically it represents an ordered sequence of items which can grow, right? I can add to, or shrink, that I can take away from. Okay? And so, like an array, it's ordered, right? So there's an index value associated with every element in my list. So I have a 0th element in my list, all the way up to an n-1 element in my list, where n is the size of the list. And the basic operations of this data type are, well, first of all, we need to be able to create new lists that are empty, right? So that's one thing we need to be able to do. We generally want to be able to insert to the end of a list, extending it, making it one larger, right? We will also want to be able to insert a new element at a particular position, moving everything down that's past that position. So those are kind of two versions of insertion. One is basically a special case of the other, right? Obviously, just like we want to be able to get things out of an array, we want to be able to get things out of a list. If I have a list, I want to be able to ask for a particular element in the list by its position. Generally, I may also want to remove an element by its position. That's often part of the behavior of a list as an abstract data type. Sometimes we want to be able to remove the first occurrence of a particular element. Like I don't necessarily know the elements in the list, but if it is in the list, go find it and then take it out. So that's another common operation I don't have listed here, but a common part of what most list implementations will provide, or most list definitions will provide. I need to be able to ask how big a list is. So I need to be able to query its size. A special case of that is to basically say whether it's empty or not. That's essentially the same thing as querying its size and testing it against 0, right? And this is related to what I just said. I need to be able to find a particular element in the list and ask whether or not some element is in the list or not, and if it is in the list, at what position, right? All right, so that's my, that's generally the behaviors that we associate with the list as an abstracted data type. And we can define in Java, right, if we want to model this idea, we can define this idea as a generic list in Java, right? So we're going to do this without knowing the element type. So we're going to use those angle brackets with a placeholder so that we can define our interface with respect to some type that we'll provide at the time that we use it, right? We're going to define it generically. One of the things we do when we study data structures is to be like, there's a difference between using a data structure and programming a data structure in order to get your program to work and make it do what you want it to do, and being able to reason formally about a data structure, right? And so in this class, we're going to do a little bit of both, right? We're going to talk about some of the classic data structures in computer science. We're going to talk about it more, on the one hand as an abstract idea and use the mathematical tools of axiomatic specification in order to be able to reason about that idea, right? That has nothing to do with programming. It has to do with essentially math, discrete math, right? And there's the companion of that is once we understand the data structure well and rigorously, then we're going to be able to express that, realize that data structure in a specific implementation and use our analysis in order to be able to confirm that our implementation matches the formal definition of the data type that we've developed, right? So an axiomatic specification is a formal way of specifying the behavior of an ADT. And it essentially provides a way of reasoning about the operations on that data type and specifying relationships between those operations in order to then be able to to understand that data type and be able to test an implementation against those properties that we were able to derive through this axiomatic specification. There are 3 steps in developing, an axiomatic specification of an ADT. The first, right, is to develop a functional specification of the operations itself, right? And we'll talk about what that means in a second. Like, basically define the behavior as a list of functions that operate on the ADT. This is going to be very closely related to the list of methods that we include in the interface, right? And then we're going to identify which of these operations are canonical, and then we can, from that point, start to derive axioms, right? It's a lot like geometry. We start with the definition of a point, and from that, we can say something about how 2 points make a line, and from that, we can say how 2 lines either intersect or don't, and then derive properties of parallel lines versus intersecting lines, and then derive properties of triangles, et cetera, right? And it's all built on these underlying definitions, these axioms of geometric properties of kind of the base thing that we built all this on, right? And so the same kind of idea is here. We want to be able to reason about how an abstract data type works by identifying which of its operations are canonical and then deriving axioms that tell us statements about the data type for how those operations interact. All right. Okay. So let's start with our functional specification of list of E, right? So remember angle bracket E, angle bracket, that just means that we're going to now be able to use this placeholder everywhere we are going to need this type name that we don't know until we actually use it, right? So it could be a list of strings, it could be a list of scanners, it could be a list of arrays, it could be a list of whatever, but it doesn't matter what it's a list of when we talk about the list behavior, and so we'll just use the letter capital E as a stand-in for that type that will be provided at the time of use, right? So a functional specification of an abstract data type basically defines what functions operate on that data type, and essentially are almost like a method signature, right? They're generally defined in this functional, we generally use this functional notation that we borrow from essentially discrete math or set theory, and we basically say, okay, the new operation, right? And in this functional style, it's stateless. In other words, the result of these functions is a new thing. Whereas when we implement it as objects, we're probably going to mutate our objects. We can talk about implementations that that mutate or don't mutate, but in general, we'll probably implement these things in a way that is object-oriented and not necessarily functional. But the way we analyze the idea of the data type is through this functional specification. So the first function that I'm going to specify as part of my ADT is the new function, right? And the new function says, if I have if I invoke the new function, the result of that will be a list, right? That's what this notation means, right? INS stands for insert, and it basically says if you take a list and an element and an integer, then you'll get the result will be a new list. Right? That's the the function of insertion is defined on the domain of lists crossed with elements crossed with integers that represent indices and creates, right, a new version of the list with that element inserted at that position. Right? REM, that's going to stand for remove, right? If I take a list and give it it's the domain of the remove function is the domain of all lists by all integers, right? And the result will be a new list, with the idea being that that new list will have that index removed, right? Same thing with get, right? The domain of that function is a list of all lists crossed with all possible integers, and the result of that is going to be the range of that function, right? What it could produce is the element at the element e at that at that position, right? Find, right? Let's say I define a find function, which basically says you give me a list and a particular element, and I come back and I give you the index, the int, where that element is, right? And then size says, you give me a list, and I turn that into a natural number, right? In other words, I'll give you back the size of that list. It's a natural number because lists can't have negative length. It can be empty. It can have 0, right? You have 0 elements in it, but it can't have negative elements in it. And then finally, I have this empty operation which says, okay, you give me a list, and I'll tell you true or false whether or not it's empty. Now, I've defined these operations on these domains of lists versus lists crossed with integers, etc. But nowhere in this specification have I actually defined the behavior, right? I have an idea, right? I mean, that's the point. We understand what we want these things to do, but how do we formally show that the result of inserting a new element at a particular spot is a list that has a size greater, that is the old list but +1, right? It's those kinds of relationships between these operations which capture the formal semantics for how these operations interact. Right? And that is the axioms that we're trying to develop. Right? So here's my functional specification of my list operations, which just tell me the domain of each of those functions and their result. Now I need to come up with the axioms. Step 1 is to find which operations are canonical. Right? I have to reason about these operations and decide which ones are canonical versus which ones are non-canonical. What do I mean by canonical? The canonical operations are the minimum operations from my specifications that is needed to produce any given instance. Right? So for example, let's say our list is 3, 5. Right? It's a list of integers. The first integer is 3. The second integer is 5. There are lots of ways I could have ended up with this list. Right? I could have taken a new list, inserted 8 at the 0 position, then inserted 5 at the 1 position, then inserted 3 at the 0 position, and then now 8's at the 1 position because I inserted 3 before it, and now removed the thing that's in the 1 position, which happens to be 8, and now I'm left with a list that starts with 3 as the first thing, and then 5, right? That sequence of those operations will result in a list of 3, 5, right? Another way I could have created this list was to start with a new list and then insert 5 at the 0 position and then insert 3 at the 0 position for that result and moving the 5 over. That would have generated the list 3, 5, right? Or I could have started with a new list and inserted 3 in the 0 position and then inserted 5 in the 1 position, right, the last position, right, after the 3, and that would have been a list 3, 5. Or, and you can see where I'm getting at this, right? There's lots of different ways I could have gotten to this, this list 3, 5. But which operations did I absolutely need to have in order to create the list 3, 5, right? The first version and the last version, the removes, right? Like, yes, these are sequences of operations that will generate this list, but all the remove operations that are part of those sequence of operations aren't really necessary, right? They just kind of counteract insertions that I'm just going to delete later in order to then get to the list I want, right? And so if I really think about it, I never need the remove operation in order to create a list of any given sequence of elements, because if I can create lists and I can insert things, then why do I ever need to remove things, right? Every possible list is possible through some combination of new and insert. I don't need remove, right? Similarly, I don't need size, I don't need empty, I don't need find, I don't need all those other operations. I don't need them in order to create any given instance of a list, right? The only things I absolutely cannot do without is new and insert. If I don't have new, then I'm dead in the water to begin with. I can't even create the list to begin with, right? If I don't have insert, then I'm dead also, because I can't make a list with any particular sequence of elements, right? So in this case, new and insert, those we identify. Those are the canonical operations. They absolutely must be required, right? They are required in order to create any given list. Once I've identified my canonical operations, I can start to define axioms of behavior. And usually the way, and now this is basically theorem proving, right? You can start to prove different theorems about lists by defining what the result of combinations of operations are. The first thing you need to do, right, the first axioms you start with are by applying the non-canonical operations to the result of each of the canonical operations, right? So the very first set of axioms, right? So the fundamental canonical operations, I need to have those, right? I just have to have them, fine. And then the axioms I can start to define from that are, what does it mean? Like, what is the result of taking the result of new and then removing the ith element? Right? Like, and as you reason about this starts to formally define the behavior of the list, and now you can prove these things, right? Once I define what these axioms mean, now I can combine those axioms into bigger statements, other axioms or other kind of statements of proof about how this list is going to behave. So let's start with the ones on the left, where we are applying remove, get, find, size, and empty to the canonical operation of new, right? So let's think about what it means to remove the ith element of a new list. First of all, does a new list have an ith element? No, right? A new list is empty, right? And so remove and get, right, aren't even going to work, right? So you know, the result of removing the ith element of a new list or getting the ith element of a new list is simply error, right? And that's okay, right? You can say, hey, this is an error condition, right? This combination of operations should result in an error, or it does, you know, or you know, is you know, not allowed, right? But other things are, right? I know that if I try to find an element within a new list, the result is false. It has to be. There are no elements in a new list, and therefore, if I try to find any given element in that new list, it's going to come back false. So I can define that. That's a well-defined axiom, right? Similarly, the size of a new list is 0, and the test for a new list being empty is true. And it's those, now I have these axioms, I can use those axioms to develop other axioms, right? The other set of things are a little bit more interesting. So remember, here we assume we have a list L, and now we are inserting into that list L some element E at some position I, right? That is the form of the insertion command. That is one of the canonical operations that I can do on a list. And now I'm going to apply the non-canonical operations on the result of the canonical operation, right? So you'll see I did it twice for remove. I did it once where J, like the idea here is J doesn't equal I, right? And I did once where I does equal I, like so. I take the result of inserting E into list L at position I, and the result of that canonical operation, I'm now saying, okay, if I apply removing the ith element, what does that mean? How are those things related, right? And similar with get, I have a version where I'm applying that where J doesn't equal I, and one where I'm using I'm using the I that I used in the canonical operation, right? Similarly with find, I have an axiom where I'm applying the find for finding E1 into from a list that is the result of inserting E1, and another one where I'm finding E2, which presumably does not equal E1, where in a list where I'm finding where I inserted E1, and then size of the result of inserting something into a list L, and then whether or not a list that has E inserted to it is empty, right? All right, so. I'm going to give you let's see here. Well, we have 10 minutes, so yeah, sure, we'll do a little active learning here. Give you 30 seconds to think about what kind of expression you can prove, right? That, from the, how we want a list to operate, what is the right-hand side here, right? Can you come up with an expression on the right-hand side which is equivalent, and essentially captures the behavior of a list? So I'm going to give you 30 seconds to think about it, and then we'll look at the answers on the next slide, or at least some of the answers. Feel free to talk to your neighbor. All right, let's see what I have. We have pretty easy answers for most of these. So let's look at the ones that involve, except for the ones where we have I and J not being the same number, right? We have pretty decent, we understand what these, what should happen, right? If I take the result of inserting element E in position I and then remove position I should get back the original list L, right? That is the axiom. That defines the correct behavior for the data type, right? Similarly, if I insert element E in position I into a list, right, and then take that resulting list and retrieve I, oops, that should be E. Right? Then I will get back E. That makes sense, right? If I try to find E1 in a list that is the result of inserting E1, then yes, I should get back true, right? I will get back, I will find that element, right? Actually, I screwed that one up too. If I find by element, my functional specification said that I should get back an integer. I should get back its position. And so really, this should be, what should this be? No, not false. I, right? If I'm finding E1, if I'm finding the position of E1 in a list that where I inserted it in I, then I should get back I, right? Similarly, if I find, if I try to find E2 in the result of a list where I inserted E1, there is, there is a correct behavior. It's the same thing, right? It's finding that is the same thing as finding E2 in the original list. It doesn't matter that I inserted E1. That's not what I was looking for. E2 might be in the original list, or it might not be, but the answer to the left-hand side is the same thing as the answer to the right-hand side. So these are basically I'm starting to derive the various properties of our AskStrav data type as this axiomatic behavior. Just like we do, we did the same thing for they did the same thing for algebra, right? X plus y equals y plus x. That is a property of addition, right? And we can talk about addition and reason about addition through its axiomatic properties. Same deal. We can talk about the operations on a list through axioms that we can formally and rigorously define via this kind of an axiomatic specification, this kind of analysis, right? Like if I try to find the size of a list which is the result of having inserted E at some position, it's the same thing as the size of the original list plus 1, right? If I ask for whether or not a list is empty, since I've just finished inserting something in it, I know that that has to be false, right? It can't be empty because I'm doing that operation on something that I know just had the insertion operation done. And so this helps me define the axiom of a list that just went through an insertion operation can't possibly be empty. And you can start combining these axioms into new other axioms and start to create more complex statements about lists, how they behave, and how these operations will affect the list. We can take these as doing this kind of axiomatic analysis on an ADT is a very good way of then developing testing code for your implementation, because now these give you a blueprint for, hey, if I have an implementation of a list, if I want to make sure it's correct, I can write code which tests each of the axioms to make sure that the correct answer is that these things are correct. Okay, let's go back to the ones where I insert and get from a list where j doesn't equal I. Here, it gets a little bit more complicated. It will depend on the relationship between j and I, right? If I insert, if I'm trying to remove the jth index from a result of having inserted element E in position I, and j happens to be less than I, then it's exactly the same as flipping those two operations around, right? This is an axiom of behavior that I can reason about. If I remove j from the original list and then insert E in position I minus 1, then that will be the same thing, right? And that makes sense because here, since j is past I, right, or j is less than I, basically when I removed the jth item from the original list, everything past j went down 1, and inserting into that result at I minus 1, the element e, will do the exact same thing as inserting first and then removing, right? And the same kind of thing with get. If j is before I, then getting the jth element from the result of inserting element e at position I is exactly the same thing as getting the jth element from the original list, because j is before I, and the insertion of element e at position I, which is past j, doesn't affect any of the indices that are before I. And so here we can see that we're now formally defining things that we understood about a list informally, but now we have an algebra for it, if you will, right? And so, informally we know if we insert at position I, everything past that point in the list gets pushed over by 1. Here is the proof that works, right? Here are the axioms that must be true that reflect that behavior. And then we can see that almost exactly the same thing for when j is past I, except it's kind of flipped around, where now inserting at I is this. It doesn't matter which order I do this operation. I can remove j, and then insert at I, because I is before j, and it doesn't matter if I do the remove first or second, right? I don't have to adjust I. But now to get the jth element from the result of inserting 1. That's the same thing as getting from the original list, but at j minus 1, because the insertion part is going to push everything past I over 1. And so what I'm asking for on the left-hand side, if I want an equivalent statement on the right-hand side, then I have to adjust j by 1, right? So it's that kind of formal specification of the behavior of an abstract data type that allows us to reason about it in some rigorous way. Now, we rarely do this with the data structures we design, because look, if you're a theoretician, if you're writing some heavy duty, you're trying to prove program correctness. There are computer scientists which really take this very seriously, and they develop all of these frameworks for axiomatic specification and what it means for program correctness, and be able to prove things about programs by deriving their behavior from the underlying axioms. So there is a giant field of computer science that is very much concerned with this kind of rigorous thinking, and we should be able to do this with the basic data types, and you should have some idea for why and what is involved in axiomatic specification. But in general, we just care about how to implement the damn thing, right? And so that's the theory of it. Then there's the practical aspect of actually implementing a list, which the behavior of the list is completely separate from. So there are two main approaches for implementing a list. One is by storing the elements in an array and making that array bigger as needed. And the other is by storing each element in its own structure and having each element link to the next element in the list. So we will do the array-based one on Thursday. The linked list version we'll talk about, but then it'll be your job to implement as the next homework assignment, which will come out later tonight, maybe tomorrow. And we'll pick it up there on Thursday.